Sage report for our last one due today. We've got Sages on God for Friday, which should be fun. Short paper number 3 is due next Monday. And then on Monday, we're going to get started with our last unit, which is going to be Aristotle on friendship. All right, so today I've got Aquinas' arguments up, locked and loaded, but we've got to finish up a bit more on that fine-tuning. So I'll switch over to the fine-tuning presentation here. And so we'll finish up the fine-tuning, and then we'll get going with Aquinas for today. Okay. Cockpit going. All right. So fine-tuning argument. All right. So we've talked about chancy explanations. We did the monkey warm-up idea, and the monkey warm-up tells us that extremely unlikely explanations are bad explanations, and so we prefer the more likely explanations to the less likely explanations. Okay. We've also talked about necessary conditions for life. So human life and life in general is a bit fragile. There has to be certain sorts of conditions in the universe for life to be possible. It can't exist in every sort of set of conditions. The conditions have got to be a certain way to permit life. So we'll call those the necessary conditions for life. Okay. But then we started talking about one of these arguments, a sort of fine-tuning argument here, which is the improbability of a low entropy universe. So we've talked about entropy quite a bit. And the basic idea here is that the universe has to have sufficiently low entropy, that is to say high order, for a life-permitting universe even to be possible. I don't know if I talked about this in this class or another class, but you can actually measure the energy and power density of various objects in the universe. And so stars, because they're basically nuclear bombs contained by gravity, have a very high power density. And so they're putting out tons and tons of energy, using tons and tons of energy. But pound for pound, the human brain is the highest energy or power density object in the entire universe. It's even more than stars. So, of course, a brain is tremendously smaller than a star, but if you measure it pound for pound, the brain is actually processing more energy than any other physical object in the universe. And so what that means is that in order to have complex and highly ordered things like brains in your universe, you got to start out with a universe that begins with a sufficiently high order and a sufficiently low entropy. So basically, Roger Penrose has calculated what's the chance that randomly a universe with this sort of order would be produced, and it's this: 10 to the power of 10 to the power of 123, which I think I told you this. This is how physics says no. Okay, these sorts of things are not physically possible in our universe. They're so unlikely as to basically be physically impossible. Okay. So the basic argument here that is human life is possible only if the universe has sufficiently low entropy, sufficiently high order to do work, like brain work. But it's exceedingly unlikely that random mindless physical processes will produce a universe with that low entropy. So random mindless physical processes don't give us a good explanation for how our universe is possible. Okay. All right. So there's the entropy argument. Now, the next thing we're going to talk about is sort of the more famous fine-tuning argument, and it has to do with the fine-tuning of cosmological constants. So we're going to start out talking about what a cosmological constant is, and then take a look at how they're fine-tuned, and then what could explain this fine-tuning. Okay, so cosmological constant. So what the heck is a cosmological constant? It's going to be a number that controls the equations of physics. Okay, so let me do a little basic equation that you might maybe have done in physics or chemistry. So good old pervnert, N-R-T. Okay, give me a thumbs up if you've dealt with pervnert before. Any of you? Dominic says the pervnert. Listen, no pervnert. Okay, pluses and minuses. Okay, so some have, some haven't, right? So this is what's known as the ideal gas law. Okay, and so it describes the relationship between three variables: the pressure of a gas. So if you blow up a balloon, and there's the gas is exerting pressure, which is what expands the balloon. So the pressure of a gas, the volume of that gas, and the temperature of that gas. Okay, and so pressure and volume are inversely proportional, and pressure and volume are each going to be proportional to temperature. So it's like this: if you make the temperature go up, if you heat the gas, either it'll expand, or if you're keeping it in a fixed volume, then the pressure is going to increase. So this is why things explode when, like, if you heat them up a lot. That's why they might pop, because the pressure is expanding. Okay. Well, N here is going to stand for the number of molecules that you have in say, like in a balloon. But then R here is simply the gas constant. Okay, the gas constant is this. I think it's called Boyle's constant. It's been a long time since I've done that, but anyway, Boyle's constant. I believe that's right. Parentheses, scare quotes. I'm not sure. In any case, look. This constant here, some number like 8.141, I think that's right. Well, how do we know that? Because we measured it. We did a bunch of experiments with pressure, volume, and temperature, and we know how many molecules are going to be in a particular gas. And then we see that they're proportional. So when the one goes up, the other goes up. When the one goes down, the other goes down. Okay, we measure these relationships, but then they scale by this number here, the ideal gas constant. And why is this number the way it is? We have no idea. It's just 8.141. We're able to measure it, and it does set the relationship between these variables. So it controls the equations of physics. But there's no physical reason why it has to be this number, or at least for some of the constants. Now, this one might be explicable in terms of more fundamental things, but at least some of the constants in physics, there's no physical reason why they need to be that number in particular. So here would be examples of just set cosmological constants. Things like the speed of light. So this is, remember, 3.0 times 10 to the 8th meters per second. Why is the speed of light this number? Remember, we've played with this before. Like, wouldn't it be more fun if it were like 7 or 27 or 81? That's a pretty number. Why not those numbers? And there's no physical reason why it's this rather than this or this or this. Okay, so we know what it is, and it is a certain constant, and it controls, for example, like, you know this one, right? E equals mc squared. So this says that the energy of a thing is equal to its mass times the speed of light squared. So this is Einstein's equation here. And what this means is that the proportion between the energy of a thing and its mass is going to be scaled by the square of the speed of light. How on earth does that equation work? And where do we get the speed of light constant from? Well, we just have to plug in 3 times 10 to the 8th meters per second, and it works for everything. So there's actually some really cool articles called "The Unreasonable Effectiveness of Mathematics and the Natural Sciences," and this is one of those examples of the beauty and elegance of equations. But it's scaled by the speed of light constant, and it's just that. It's just that number. There's no physical reason why it has to be that number. So there are other constants like this. Planck's constant, h bar, which has to do with like the fundamental sizes of things, and then the energies of things too, how much they can differ from each other. Gravitational attraction constant. So this has to do with two bodies and how they're attracted to each other by the force of gravity, you know, like the Earth and the Moon, and how they stay in each other's orbit and attract each other that sort of way. So the gravitational constant measures that a degree of force between bodies gravitationally. Strong nuclear force, weak nuclear force, rest masses, charges of electrons, gas constant, these sorts of things. Okay, so how atoms hold together, how they interact with each other, how plus and minus charges repel each other. Okay. So these are the kinds of constants that we can measure by doing experiments. But once we plug them into our equations, they just sit there as a constant. They don't get explained in terms of further variables. Okay, so we know what these constants are, but there's no physical reason why they are the value that they are. Okay. Now, why does this stuff matter? Let's see. Okay, so I want to make this point right now. This is what the fine-tuning argument takes for granted, is that when it comes to something, say like the speed of light, okay? So we know that the speed of light is right here, 3 times 10 to the 8th meters per second, okay? But this 3 times 10 to the 8th meters per second sits on a gradient, on a spectrum of other speeds that the speed of light could have had. So here's my favorite over here, 81. It could have been up here, 27. It could have been, 1 times 10 to the 8th meters per second. Or it could be way up here. It could be like 3 times 10 to the, 100th meters per second. That would have been a really fast speed of light. So we know that as a matter of fact, the speed of light is right here at 3 times 10 to the 8th. But according to physics, there is literally no reason why in our universe it couldn't have been here, or it couldn't have been here, or it couldn't have been here. Okay? And this is true for each one of these constants, the speed of light constant. We know it's here, but it could have been in any of these other places, and there's no physical reason why not. Planck's constant. We know it sits here on its spectrum, but it could have been all these other numbers too. Okay, so all of these constants are like this, where they sit on a particular spectrum. They are a particular number on that spectrum, but there's no physical reason to have actually been in these other regions of the spectrum either. Okay, so hang on to this idea that these cosmological constants could actually sit anywhere. Given the laws of physics, they could be anywhere. There's no physical reason why it isn't that, but we measure them to be precisely here in our universe. All right. Okay. Now, with that idea in the background, let's now talk about what fine-tuning is. Okay, so fine-tuning occurs when one result A is finely tuned for another result B, just when B is possible only when A occurs within an exceedingly narrow range of values. So a decent example of this would be something like harmonic resonance in music. Okay, so suppose we've got 2 tuning forks here. Okay. All right. So maybe you guys have seen this before in physics. In like a physics demonstration, it's pretty cool. But resonance is a phenomenon where if 2 tuning forks are dialed in to exactly the same pitch, say something like A equals 440 hertz. So that means that the tines of the fork are vibrating back and forth 440 times every second. Okay, so that's the tuning that often is used in like orchestras and stuff like that. The note A goes to 440. Okay, so if you've got one tuning fork that's dialed into A equals 440, and then you've got another tuning fork that's also dialed in to A equals 440. Okay, then if Jeffrey here takes his grubby little hands and taps this tuning fork and makes it chime, so this is its chiming here, then even though Jeffrey has not tapped this other tuning fork here, it'll start to go. So this one is in resonance with the other one, so that the vibrations in this tuning fork, call this one number 1, is going to cause vibrations over here in this tuning fork number 2. And these 2 tuning forks are in resonance with each other. Now, this phenomenon of resonance happens only when the 2 tuning forks, number 1 and number 2, are dialed into exactly the same frequency. If this guy, number 2, is over at like 441 or 442, or even worse, 444, something like that, then Jeffrey can tap number 1, and this guy is not going to vibrate at all. It's just going to be dead. Okay? So resonance is a finely tuned phenomenon. The result of resonance happens only when they're exactly at the right values with each other. If it's a little bit higher, it won't work. If it's a little bit lower, it won't work. So if we've got this spectrum of values here, it's finely tuned because resonance happens only when they're both at 440. These other values don't work. These other values don't work. Only exactly here. Okay? So that is an illustration of fine tuning. Okay, so now this is what we do. We take this idea of fine-tuning and we say many cosmological constants are independently finely tuned for life. Okay, so let me illustrate what that means. Okay, so let's go ahead and take our spectrum here, and this again will be our speed of light. Okay, so speed of light is again going to be our 3 times 10 to the 8th meters per second. Okay, now what physicists do is they'll play around intellectually. They'll play around with the equations of physics. So they'll do things like this. We've got up here, E equals mc squared. Okay, and so what they can do is what would a universe look like if this equation were still to be true, E equals mc squared, but the c here, the speed of light, wasn't 3 times 10 to the 8th meters per second. It was 3.1. So we just boost up the speed of light a little bit, and then we see what happens to this matter and energy proportion. And the speed of light occurs in lots and lots of other physical equations, okay? So what they do is they play around with the numbers a little bit and see what happens to their equations and see what the equations predict about the way the universe will be. Well, what happens? What happens when we play around with these numbers a little bit, when we move the speed of light a little bit over here, or when we move the speed of light a little bit over here? What happens? And the answer is death. Death on all sides, okay? Death over here. Death over here, okay? If you, these are skulls, by the way, if that wasn't clear. Okay, so here's the deal. Death actually occurs right next to the speed of light. And death also occurs on the lower side and also on the higher side, okay? So if you tweak the speed of light just a little bit to the left or a little bit to the right on the spectrum, the physics of the universe becomes absolutely catastrophic. Okay, so the only way life can be possible is if the speed of light is exactly here. It can't be higher, it can't be lower. And not only for the speed of light, but also the gravitational constant, also the electron mass, also the proton mass, also the weak force, also the strong force. Okay, lots and lots of these, I think it's like 20 different cosmological constants are finely tuned, such that the place where they're at is compatible with life, but a little bit lower or a little bit higher results in death. Okay, life is not possible under those conditions. Okay, and so this is the idea of the cosmological constants being finely tuned for life. Life is possible just when those cosmological constants occur within an exceedingly narrow range of values. Okay. Okay. So, yeah, I'm just saying the thing I said before. Human life is possible only if gravitational weak force constants take on certain values, strong nuclear force, proton, electron mass, and then you got to have the right sort of carbon and stars to make molecules for life too. Okay. But this is one of the very important points that the fine-tuning argument wants to make. There's absolutely no physical reason why the constants must take those values. They could have been wildly different within an enormous range. So it's like this. Like we set up the speed of light constant, and we find, oh, it's right there, which is where it's finely tuned for life. And then we set up the weak force constant, and we find, oh, it's right there, which is also finely tuned for life. Then we set up the next one, the gravitational constant. We find, oh, it's right there, finely tuned for life. And so you do this for like 20 different constants, and they're all at exactly the value that is needed for life. Okay, and so many physicists, both theist and atheist, they took a look at all these different constants, and all of them occur at exactly the life permitting point. Okay, and they look at this and they're like, what the heck? There's no physical explanation for why these values are what they are. We just find them here, 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 for life, for life, for life, for life, for life, for life, for life. Okay, and so physicists look at this and they say, this is a remarkable coincidence that the constants have the values that they do. Okay, so with this as our backdrop, then we're going to set up the fine-tuning argument proper. And so the fine-tuning argument proper, I like to illustrate with the analogy of the fussy crab. So here's the fussy crab. I'm going to go ahead and draw him. I love drawing this guy. Okay, he's got his little bow tie, and then he's got his little crab pinchers. Here he is with his crab pinchers. Okay, and he says, I pinch. So there's our fussy crab. Okay, now here's what you know about fussy crabs. They're just like hermit crabs, and they make wonderful pets, but they're fussy because they can survive only if the temperature is 72 degrees plus or minus 1 times 10 to the minus 50th degree. So here's what I mean by this, okay? So like if you've got your fussy crab and the temperature strays upwards to 72.1, dead. The fussy crab is gone. He can't survive. Okay, if you put the temperature at 72.01, oh no, he's dead. Cannot work. It needs to be way closer. It needs to be exactly 72 degrees. So if it moves just a tiny bit upwards or a tiny bit downwards, this fussy crab is absolutely dead. Okay, so he's fussy because he can only live in a very particular temperature. Ridiculously narrow range of temperature. Okay, now you learn this. a fuzzy crab is alive and well in a house somewhere in Bismarck. Okay? But you don't know what time of year it is in Bismarck, and you just know that there's a fuzzy crab in there. All right? Now, if you know this, you know these background facts about fuzzy crabs, and then you learn that there's a fuzzy crab that's alive and well in a house in Bismarck. You basically have two explanations. Okay? You could either say the fuzzy crab is kept alive by chance, or the fuzzy crab is kept alive by an intelligent being. Now, which of these is the better explanation? Well, think about this argument. A fuzzy crab survives only if the temperature is kept in a ridiculously narrow range. But it's exceedingly unlikely that random fluctuations of temperature in Bismarck will keep the temperature in that range. Like, for example, today it's raining, but tomorrow we're supposed to get like snow and stuff in Bismarck. It's like this fake spring that we always get. And you know how Bismarck is, right? Up and down and up and down and up and down. So do you think that this sort of temperature fluctuation is going to keep a fuzzy crab alive in Bismarck? You're going to say, heck no. Okay? Random temperature in Bismarck is not going to keep that fuzzy crab alive at exactly that 72 degrees. Okay? So what this means is that chance is an exceedingly unlikely explanation. And so any explanation that's more likely, namely an intelligent being, is going to be a way better explanation. So there's some, very particular, he's probably like a professor or something at UMary. Maybe it's Dr. Ronderos, who loves all sorts of living things. Who's got a very particular thermostat who can keep alive this fuzzy crab dialed into exactly the correct range. But only an intelligent being could compensate for the random fluctuations and keep the fuzzy crab alive. Okay? All right, so that's an analogy for what's going on in the fine-tuning argument. Okay, similarly, is our life-permitting universe a product of chance or an intelligent being? Well, it's exactly the same here. The speed of light is dialed into this particular value. And if it's a little bit higher or a little bit lower, it's death for us. We can't survive that. Okay? So are we in this universe as a product of chance or as a product of an intelligent being? And so the argument is that it's going to be exceedingly unlikely that mindless random fluctuations would produce the cosmological parameters that are finely tuned. That would end up exactly here. So, like the fuzzy crab is best explained by an intelligent being keeping it alive, we are best explained, and life is best explained by a universe produced by an intelligent being that somehow wanted us around. Okay. All right, let's pause. How you guys doing? If this makes sense, give me a thumbs up. If it doesn't, thumbs down. And give me questions. Give me some love in the chat box here. Round of applause from Jonathan. Oh man, that's good. Probably, I'm a little skeptical about that because you can always do better. Good questions. What do you want to ask about? All right, guys. Well, it seems like you're pretty good. What should we do? So there's some more stuff in here. There's some stuff about multiverses. So some people have the idea that the reason why the universe is so finely tuned is because there's a multiverse generator. So maybe there's some sort of cause in the universe that is generating billions upon billions of universes. And so there just happens to be one with the right parameters. Just like if you play enough cards, you'll get a royal flush at some point. But there are some objections to this multiverse hypothesis. And has to do with, even this multiverse seems to be finely tuned itself. It also seems to be not a very simple explanation. And also it needs to have a beginning in time. So there seems like there has to be a creator for the multiverse generator as well. Okay, but I'd like to spend a bit more time on the Aquinas argument. So I'll let you guys read this yourself. I'll be posting all these online. Also, it's pretty well explained in the reading too. Okay, so let's move on to talk about Aquinas' 5 ways. Okay, so let's get started here. I'll do a little sketch on types of argument for God's existence. We'll summarize Aquinas' argument and then talk about the argument for motion. Okay, so in the world of the philosophy of religion and the philosophy of God, there are 2 broad families of arguments for God's existence. Some of them go from reason alone. So basically stuff that you could know just sitting in your armchair and just reflecting on basically your own thoughts and concepts. So some arguments for God's existence are based on reason alone, And some of them are just are called ontological arguments. Ontology is the study of being and existence. And so these sorts of ontological arguments are based on God's nature alone. So actually St. Anselm gives a famous ontological argument. He talks about God as being that than which nothing greater can be thought. So that comes from God's nature, God having this kind of greatness that somehow must exist in reality. Other reason-based arguments would be mathematical arguments, which are based on abstract argument or abstract objects. So some people think that things like numbers or sets or geometries or symmetries require a mind in which they must be grounded, and this mind must have certain sorts of properties that make it a divine mind. So they're actually mathematical arguments for God's existence too. So these are based on reason alone. But what we see in Aquinas' arguments that we read for today is arguments that are based on both reason and a certain amount of experience. So observing the world a little bit and then reflecting on the world. So these types of arguments are sometimes called cosmological arguments. There's another family of teleological arguments, and there's a family of moral arguments. So we'll take a look at these arguments from reason and experience. So here's experience-based arguments for God. So the general structure is going to go like this. One premise is going to observe something about the features of the universe. So it's going to say, hey, look, the universe has a particular feature, which we'll just call X. And you can slot in any sort of, lots of different kinds of features X that'll make for different kinds of arguments for God's existence. So that's the first step, is a kind of observational step. And then the next step of the argument is going to say, hey, the universe couldn't have that feature X unless there were a God to explain that feature or account that feature or cause that feature in the universe. So God has got to exist. So cosmological arguments are going to fill in the X in a particular way. So it's going to say, hey, look, the universe has a feature like change, or it has a feature of causation, or it has a feature of contingency, which is the possibility of being or not being. Degrees of perfection. Some things are better than other things. And then, or the beginning in time. So actually, some of those Spitzer arguments about the beginning of time would be basically a cosmological argument. And so, hey, look, the universe couldn't have a beginning in time unless God exists. Or there couldn't be change unless God exists. So these would all be different varieties of cosmological arguments for God's existence. Teleological arguments have to do with order and have to do with purpose. The purposes of things, because the telos in Greek means the goal or the purpose of an object or a being. So here, a teleological argument would say, hey, look, the universe has minute biological order. So there seems to be beautiful purposes to the eyes, to the heart, to the nervous system. Okay, and these things are minutely ordered towards certain ends for that creature. Also, we see cosmological fine-tuning. So you can do a teleological arguments based on living things, or you could do it based on the cosmological constants of the universe. And both of these seem to show a purpose to the universe, and so this purpose requires a certain sort of purposer, an intelligent designer. And the last one would be moral argument. So you could say, hey, look, the universe is a place where there are things like moral obligation, or moral goodness, or even moral evil. Some people argue for God. You know, it's kind of ironic. Some people say evil is an argument against God, but some people use evil as an argument for God. It would be something like this. There couldn't be evil unless there were goodness, but there couldn't be goodness unless there were God. And so even the existence of evil is an argument for God's existence. Now, that's a bit of an IOU. You got to fill that one out quite a bit. But so these are based on features of moral reality. Okay, so we're going to focus, though, on Aquinas' argument from change, or what he calls motion, as being a really powerful one that's been discussed for a long time. So we're going to look at Aquinas' argument from motion here. So here's a basic summary of the argument, and it goes a little something like this. It starts with premise one, saying there exist some things that are moved, or basically it's this idea, change exists, okay? So the universe has this feature of things that change or things that are moved. Okay, and then these next two steps here are trying to tie the existence of change to the existence of an unmoved mover. So it's basically saying change exists, and there couldn't be change unless there were an unchanged changer. And so these are the two steps. Everything that is in motion is moved by something else. So nothing moves itself. It has to be moved by another thing. but then there couldn't be an infinite series of things moving things, moving things, moving things. There has to be something that grounds the whole change, and that is unmoved in itself. So there must be a first unmoved mover. And then this next step here equates the first unmoved mover with God, and so God exists. All right, so there's a basic sketch of the argument, and now we're going to dive into the premises and look in them in a little more detail. Okay? So the first premise has to do with motion. So what is motion, and how do we know about it? That's what we're going to look at. Okay? So here's the first premise. There exist some things that are moved. Now, when Aquinas says there are things that are moved, is it like, oh my gosh, I was so moved? It's like, no, that's not what we're talking about. We're talking about change, and change in a very broad brushstrokes kind of way. There are various sorts of change or motion in Aquinas' philosophy. And the two biggest sorts of categories of change would be change in accidents or change in essence. So remember, we talked about essential features would be the thing that features the thing has to have in order to be itself, or the accidental features are the features that we can have, like height, weight, shape, age, color, that can come and go while we remain the same. So he talks about different kinds of accidental change. So quantitative change would be change in how much. So that would be change in size, for example. I can grow, I can shrink, I can weigh more, weigh less. Qualitative change would be change in the qualities of a thing. So qualities would be things like color. That would be a quality. Also, my habits. What's my quality of character, my moral character? That would be a qualitative change. So I could be more virtuous, more vicious, something like that. Those would be changes in quality. And then locomotive change would be change in place. Okay, so here versus here versus here versus here. So that's a change in the place in which I'm existing, which is a kind of change. A change in essence is what Aquinas is going to call a substantial change. And a substantial change occurs when you start out with a little bug, here it is, and then you squash it and make it dead. Because a bug corpse is not a bug. It's something different from a bug. Bugs are living, corpses are not. So there's a change in essence. There's a change in what this thing is. And that's also a different kind of change. So sometimes substantial change goes on to change in the substance of the thing, what it is. Okay, so there's what changes. Now, how do we know that motion exists? Well, we know that through the senses, says Aquinas in the argument. So you could feel the heat, it tastes so sweet, groove the beat, see neighbors greet at 6 feet. Okay, and we are now officially Dr. Seuss. Okay, but feeling, taste, hearing, sight, okay, that's how we perceive change. So our knowledge of change comes through the senses. All right. Now, if we're going to deny that change exists, then this is going to be a very, very radical form of skepticism about the external world. But even this skepticism still seems to admit change. Because suppose the skeptic is giving his argument for that our senses deceive us and that change really is not real. Well, what is he trying to do? He's trying to lay down premises, and he's trying to change our minds. So even if the skeptic is giving an argument for his view, he's still undergoing certain sorts of mental processes, but that's still going to be a change in quality. So even a robust skepticism about change is not really going to get rid of change. And so the conclusion here is that the existence of change is an extremely solid premise. Okay, so it's not really a question about whether change exists. It's more a question about whether change requires the existence of something like God. Okay, so the next premise here is going to be the idea that everything that is being changed or undergoing a process of motion is changed by something else. So here we need to study a little bit about what change is. And so Aquinas is going to define change as being conversion from potentiality to actuality. So an example that we might use to illustrate this is we start out with a rubber ball. So this rubber ball is going to have certain actual properties, like it's going to be red, it's going to be kind of squishy. I guess, no, not squishy. It'll be more bouncy. So that it'll be red, it'll be bouncy, it'll be a certain size, okay? But then if you put this ball through a microwave, here's a little microwave, and, beep, beep, you microwave that bad boy, it's going to end up like this, a little puddle of red goop. Okay, now it might still be red, but now it's not going to be bouncy anymore. It's going to be squishy, and it's going to be a different size. It'll be a smaller size because it'll be melted and flattened out. So this is a change. we are taking this ball and we're making it different than it was before. But the way in which Aquinas is going to explain this change is what we're going to do with the microwave is to actualize some of its latent or hidden potentialities. Because even though when this ball is starting out, it's actually red, actually bouncy, and actually a certain size, nevertheless, at the same time, it is potentially squishy and it is potentially a smaller size. And so these are the sort of hidden potencies of this ball. Potencies are what a thing is able to be, but is not right now. And so what the microwave does is it takes those potencies and it actualizes them and makes this squishy, flat, goopy ball over here. And why should we think that these potencies are real features of a thing? Because this rubber ball here has certain potencies that this like ice ball over here does not have. If this ball is made out of ice, if you put the ice ball through the microwave, it's not going to turn squishy. It's going to turn into a liquid. And so this rubber ball has a potency for squishiness that the ice ball does not. Or consider a ball made out of like marble. Okay? A marble ball, if you put the marble ball through the microwave, it's not going to turn squishy because it's just going to turn hot. It might explode or turn into a powder, or it might melt into liquid, but it's not going to turn squishy. A rubber ball is going to do that though. So ice balls and marble balls and rubber balls have different potencies. And so change is going to be the actualization of that potency. Okay. So here's the idea that when a thing is undergoing change, when its potencies are being actualized, this actualization of a potency must be done by something besides the changing thing itself. Why is that? Well, here's a quick slogan that followers of St. Thomas Aquinas like to emphasize. You can't give what you don't have. So notice, a potential microwave doesn't melt the ball. So if I've got an empty box here, here's my empty box, okay? And it's filled with, microwave parts, but they're not put together. They're not assembled. This might be a potential microwave. Like it could be a microwave, but if it isn't an actual microwave right now, it's not going to do any work. So only actual things do work. Or say potential strength. Like I'm potentially stronger than I am right now. Like I work out a little bit, but I don't work out as much as I did in college. And before in college, maybe I could lift a piano, but I can't now. Now I could potentially get that strong again, but that potential strength is not going to lift the piano right now. I need to have actual strength to do actual work. Or potential riches do not buy the yacht. So like, look, I could be a millionaire. I'm like, yeah, okay, well, where's the yacht right now? So again, potencies don't do any work. Okay, so that's the first idea. If you aren't actualized in a certain relevant way, then you can't do the work of actualizing something else. Okay, so then here is the next idea. Nothing in mere potentiality can be in the relevant actuality in the same time. So here's some examples. The cold rubber ball, which is potentially hot, but not actually hot, this cold ball is not relevantly activated to melt itself. The ball can't sit there and be like, I want to be warm, I want to be warm, I want to be warm. It doesn't have the actuality that it needs to warm itself. Or consider a potential doctor. A potential doctor isn't relevantly activated to heal. So like suppose you're like in med school and you're on the way to being a doctor, but you're not yet a doctor. Well, if you don't have that training, then you can't just sit down and heal someone because you're not activated in the right sort of way. You're not actualized in the right sort of way to heal someone else. So to change someone else, to bring someone from sick to well. Or a potentially sharp knife also is not relevantly activated to cut. Now it could be sharpened, but if right now it's not actually sharp, then it can't cut anything. And it doesn't have the activation that it needs to sharpen itself. So what this means then, the consequence of all of this is that something is moved, something gets changed from being potential to being actual, only by something besides itself that is activated in the relevant sense. So the ball can't melt itself, but when the microwave is built and turned on and plugged in and actually sending microwaves into the thing, then it can melt the ball, but the ball can't melt itself. So things that are undergoing change require something besides themselves to be changed. Okay. All right. So we got this idea then that something that's undergoing change, if this thing is changing right now, Okay, it can't explain its own change. It actually is going to need something beyond itself to explain its being changed. But then suppose that this thing is being changed at the same time. Well, then it's going to need something further, and it's going to need something further. So the question is, could this series of changers go on forever? And Aquinas' answer is going to be no. A series of moved movers cannot go on forever. So unfortunately, we don't have time to go into this in its grand depth. So what I'd like to do is use the most fitting example, which is the boxcar illustration. Show you how this works, okay? So suppose I've got a series of boxcars here, like on a train. Like when you get stuck at the train tracks and there's all these cars going by and it takes forever, and but you still pull down the window because it's romantic to hear the train clickety clacking by. Okay, so suppose this set of boxcars is going on forever, and we'll just go ahead and like number them 1, 2, and 3 so we can talk about them, okay? So suppose you drive up to the train tracks and you see these boxcars going by. Now what you see is these boxcars, and each one of them is going to be what we might call a pulled puller, okay? Why is it a pulled puller? Well, because this boxcar number 1 here is getting pulled by 2, and that's what actually gives it its force to be able to communicate that pull to other boxcars down the line. So it's both pulling further boxcars, but then also getting pulled at the same time. So 2 is a pulled puller, 3 is a pulled puller, 4 is a pulled puller. Okay. Now, the question is, if we recognize that pulled pullers by themselves, boxcars by themselves, aren't able to generate motion. So 3, 2, and 1 by themselves are not sufficient. If we just cut this picture here and say, all right, do these guys by themselves explain their moving? If you just had 3, 2, and 1 together, would that be enough for motion? You would say, no, it's not enough for motion. Why? Well, because 3 doesn't pull by itself. It needs something beyond 3, 4, say, in order to get its motion, which it can then communicate to other things. Okay, so this set of pulled pullers then is not enough to explain the motion of these pulled pullers. Well, what if we just added on another boxcar? We say, oh, they're not enough by themselves. We'll go ahead and add another pulled puller on there. Would that be enough to explain motion if we just add another pulled puller, 4? And the answer is going to be no, still not enough. Well, what if we add 5? No. What if we add 6? No. What if we add infinity? No. So the basic idea is that even an infinite number, which I wrote down here, an infinite number of pulled pullers is not going to be sufficient for motion. What we actually need is a locomotive here. We need something different, which is going to be an unpulled puller. Okay, it pulls other things without being pulled itself. So it has some sort of engine, some sort of other source of motion within itself that doesn't require further pulls, but that it can generate that energy and then communicate that energy to other things without itself getting pulled. So what this locomotive analogy shows us is that you can't have an infinite series of pulled pullers explain its own motion. It needs something outside of the series that is not a pulled puller, that is an unpulled puller, in order to explain the motion that's going on. Okay, so what Aquinas is going to say is similarly for the changes that go on in our universe, the changes that go on in our universe are similarly stacked sets of changes. So an analogy that you can give, I'll do it here, the coffee cup analogy, okay? So if you've got a coffee cup sitting on your desk next to one of Alyssa's scones here it is. Okay, so if this coffee cup, starts out nice and hot, but then as time goes by, it's going to be cooling down. Well, how does that happen? The coffee cools because of air motions, and the air motions are cooling because of molecular motions. The molecular motions are cooling because of atomic motions, and the atomic motions are cooling because of subatomic motions. The subatomic motions are happening because of string motions, if you're a string theorist in physics, okay? But all of this is happening exactly at T1. It's not as if the air motions were earlier than the molecular motions, or the atomic motions were happening earlier than the molecular motions. It's all happening at the same time. So just like the boxcar all the boxcars are moving at the same time, the coffee's cooling is happening at the visible level, the invisible molecular level, atomic level, subatomic level. All of this is happening right now in a hierarchical stacked chain. Okay, and so all of these changes are happening simultaneously, but the lower level stuff is explaining what's happening at the higher level stuff all at once. Okay, but once you get down to this fundamental level of reality, the strings being, the strings can't actualize themselves. Okay, you have to distinguish between what the string is and what the string can do. And what a string can't do is bring itself into a being or keep itself in being. Strings just don't do that. Strings don't explain their own being, but they must be actual strings before they can actualize subatomic motions, before subatomic motions can actualize atomic motions, between atomic motions can actualize molecular motions, between molecular motions can actualize the coffee's cooling. So even a simple cup of coffee shows us a stacked hierarchical chain of causation existing all at once. And this fundamental chain of motions happening at more and more fundamental levels of reality is going to require, at the most fundamental level of reality, something that is unmoved in order to bring about the actuality of the motions of everything else. So this is Aquinas' insight that, actually going back to Aristotle too, that the actualizations of the potentials of things are going to require something that is fully, absolutely actual, pure actuality, which is what Aquinas is going to call God, to ground the motions that we observe and feel through our senses. Okay? All right. So that was, unfortunately, a bit pressed, but we did get through the basic sketch of Aquinas' argument. That's basically how it works. There's more slides on here, which I invite you to download this thing and you can take a look at it. I also have some objections to think through, but unfortunately we didn't have time for that today. But hopefully you enjoyed that. I'll stick around if you want to chat about this argument at all, and we'll do some Sages on God on Friday, and have a great one. Talk to you soon. Take care. Questions, guys? Anything I can go over with you? All right, Jacinta's got something. Let's see what we got. Sure, absolutely. Multiverse objection. Okay, let's do this. Okay, so let's open up a page here. All right, so let's set up a universe here. So here's a universe, okay? And this universe has various properties. So it's going to have a certain speed of light. It's going to have a certain gravitational constant. It's going to have a certain weak force constant. It's going to have a certain strong force constant. Okay, and the amazing thing about all these constants is that they are perfectly dialed in for life. Okay, so they occur at exactly the right values that they need to be in order for living things to live. Okay, so it would sort of be like this. If you were, so yeah, it'd be like this. Okay, so suppose you've got a deck of cards, you've got 52 cards, and you shuffle them up completely so that they're perfectly random. Now, what are the chances? And okay, now, yeah, let's do a scenario like this, okay? Yeah, we can do this. So suppose you've got your deck of cards right here, okay? And then poor Jeffrey is in a seat, and he's got his hands tied up by a bandit. And so here's the bandit, all right? And the bandit, here he is. Here's the bandit, okay? And the bandit has got a gun, and he's put a gun to Jeffrey's head, okay? And the bandit says, unless you deal this randomly shuffled deck of cards in perfect order, like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what is it? Jack, queen, king, ace, for all the suits in order of hierarchy. Unless you deal it like that, I'm going to shoot Jeffrey, and he's going to be completely dead. Okay? Now, what are the chances that a randomly shuffled deck is going to come out in this order? Okay? And you're going to say almost zero. Okay? There's almost no chance. Okay? So, the chances of a randomly shuffled deck turning out in this order are basically zero. And so we're going to say that is unbelievably unlikely to happen. And so we're going to say, so it's unbelievably unlikely that Jeffrey's going to live. Okay? But now, when we take a look at the properties of the universe, here is our universe again, remember? So here's the speed of light, here's the gravitational constant, here's the weak force constant, okay? When we take a look at these constants and we look at what their numbers are, it's basically like the numbers coming out as a perfectly dealt deck. Like, speed of light is fine. The gravitational constant is fine. The weak force constant is fine. The electron mass is fine. The proton mass is fine. The charge constant is fine. The gas constant is fine. It's like, holy cow, how did this happen? So physicists find this unbelievably unlikely and therefore surprising that these constants turned out to be right when they didn't have to. It would be just like dealing a deck of cards and finding the numbers to come out perfectly in order when they didn't have to. Okay? So that's the sort of background to the multiverse objection. But now let's back things up for a second. Okay, let's suppose that we have the same setup where we've got our bandit, okay? He's got his gun, and Jeffrey's in the chair, okay, and he's tied up. And now the bandit says, okay, deal this deck of cards, but I'm going to give you, I don't know, 1 billion chances to deal the cards. And if in one of these billion chances you get the numbers coming out 1, 2, 3, 4, 5, 6, 7, then I'll let Jeffrey live, okay? So now the question is, how likely is it that Jeffrey's going to live if you get 1 billion chances to deal out the cards like this? And you're going to say, actually, it's pretty good. Pretty good chance that Jeffrey will live, because if you deal the cards 1 billion times, one of these is likely to come out just randomly as the right order to allow Jeffrey to live. Okay? So the multiverse objection is like this sort of setup, where it says, there's this thing in reality, and it's a complete posit, and in principle, we could not have any physical evidence of it. But they're going to say, as a theory, let's suppose that there's this thing called, so it's going to be the universe generator, UG. Okay, so we've got this universe generator. And the thing the universe does is it randomly coughs out universes like this. Universe, 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 okay? And so it's bubbling off these universes. And so they'll talk about bubble universes. So it's like, when you've got one of those little sticks that you dip in the bubble solution and you blow the bubbles out. It's like that. So it's bubbling off these universes. And it bubbles off the universes in a random sort of way. So they all have some sort of speed of light. They all have some sort of gravitational force constant. They all have some sort of weak force constant. Okay, so all of them have this C, GFC. Okay, weak force constant. Okay, so each of them has it, but this one's a little higher. This one's a little lower. This one's a little higher. This one's a little lower. Higher, higher still, higher still. Okay, so all these numbers vary randomly in the universes. But there's going to be trillions upon gadzillions. It's just inconceivable sorts of numbers of universes being bubbled off by this universe generator. Okay, well, when you have, say, gadzillions of universes, what are the chances that one of them, this guy, has the constants that are needed for life? gravitational force constant or the weak force constant, okay? That one of these gazillions is rightly set up for life. And so the multiverse objection says, you're going to find at least one, okay? So then the multiverse says, just like it's exceedingly unlikely that in one try we would get the cards to come out, but in lots of tries we would get the cards to come out, it's admittedly exceedingly unlikely that on any one try of the universe generator we would get a universe that's set up for life. But if you give a gazillion universes, then it's actually pretty likely that we would get a universe set up for life. And the reason why we're able to observe these numbers is, well, because we're in that universe. Like, it's only the universes that are life permitting that living things could turn around and observe those conditions that are permitting, that actually permit them to be alive. Okay. So this is the multiverse objection, and it says you, Spitzer, and other people say that these numbers, finely tuned numbers, are so amazing that there has to be an intelligent designer. But the objections is say, no, there doesn't need to be an intelligent designer. There just needs to be an unintelligent random universe generator that bubbles off all these universes. And at some point, you're going to get a life permitting one just because there are so many, and random chance. If you allow randomness to work for long enough, some pretty wacko and interesting stuff is going to happen, like a life permitting universe. All right. Now, Jacinta, did you want to hear just the objection presented, or did you also want to hear more about the responses to it as well? Great. Okay. Sounds good, Jacinta. All right. Well, I'm glad that helped, and it was fun to be able to go through that. So good. I felt like I got my fix, so thank you. That's right. And you like the sciencey stuff. So this is all part of physics. And so there's this huge conversation that goes on between philosophy and physics about this fine-tuning argument. It's, I would say, in the field of philosophy today, among atheist objectors to God, this is today the most well-respected argument for the existence of God. People take this one really, really seriously. Personally, I like Aquinas' arguments better. I think they're philosophically stronger, dealing with the change which is right before us. And I think it's also a deeper and more fundamental sort of philosophy. But in terms of what philosophers actually respect today, there are definitely Christians who are developing this fine-tuning argument. And as I said, it's the most well-respected argument among atheists today, probably because, in our contemporary environment, science is sort of held up as the privileged way of coming to know stuff. And so this type of argument really does take the science very seriously, and it's predicated on some admittedly amazing results of contemporary physics. Great. Sounds good. Have a good one, Jacinta. We'll see you soon.